So let me see if I can make it big here. I put it in a presentation mode before, so okay. Now, since it's changing now for everyone, I'm going to start all over. Now, the topic is talking about, this is fitting linear model with matrices. What we did the other time, we derive how to, we did that using a different approach. And of course, using matrix to represent stuff, we enable us to get result on time. Like in this situation now where we have simple linear regression model, we're actually going to have a way to generate an equation, a matrix equation that will enable us to obtain a beta naught and a beta one. And I remember when I started, I said that this is representing, all of that in matrix form, a case in exam. And I said, okay, you know what? Y equal to beta naught plus beta 1s plus that. Can you represent that in matrix form? I expect you to give a matrix representation of Y, of the X. That very X is a design matrix. X is always going to have 1, 1, 1, 1 because of the constant. And the error, the dimension of the error is going to be the same as the dimension of Y. And of course, the beta there is a parameter, telling you we got 2 parameters to estimate beta naught and the beta 1. Now, the next thing I want to show you now is we have, do you know we can get all of that like beta naught and beta 1 by solving these 2 equations simultaneously? Okay, so when we solve the 2 equations simultaneously, we'll be able to obtain the beta naught and the beta 1. But you know what? Can we have a way to retrace our step, like to the formula used? Now, take a look at this. If you actually, if you see this in equation 1, and this guy in equation 1, and this guy in equation 2, and this guy in equation 2. If you take a look at that, what is the coefficient of beta naught and beta 1 in equation 1? It's just this guy. I tell you know that. What is the coefficient of beta naught and beta 1 in equation 2? It's just this guy. Is that you factorize them, then here you just put your beta naught cap and the beta 1 cap. Then they're going to be equal to this guy. This guy, you can put that in a matrix form, and that's why you have this. Is there any question about that? Is there any question about how? So which means, okay, so what you see now, okay, so what you're actually seeing now is this guy is the same thing as these 2 equations. Okay, I just wanted to take a look at this guy now. Now, if I'm looking for beta naught, take a look at this. If I want to go, there are 2 things here. Here, solving simultaneously, I will get beta naught cap and beta 1 cap. If I don't want to go, if I don't want to use that approach, here, I'm looking for this guy, right? Then, in ordinary equation, let's say for instance, I got 5x equal to 4, for instance, right? If I'm looking for x, what do we normally do? We divide both sides by 5, right? But here, we're looking for this guy. They are all matrices. We are not going to say we're going to divide both sides by this. But you know what we're going to do? Can somebody suggest what are we going to do? Go ahead. Exactly. Send me a message for extra credit, okay? So I'm going to get the inverse of this guy, right? And I'm going to pre-multiply, not post. There's a difference between pre-multiply and post multiply. So I'm going to multiply this guy by its inverse. And I'm also going to do the same thing here. Okay. So that is what you're actually going to see. Now, if you have that guy now, okay, take a look at this. Oh, give me 1 second. Okay. Now, what the formula is telling me now is this is the formula, which means that other guy, this guy here, S transpose that is this guy that we said we need the inverse. And how did this guy form in the first place? It is a design matrix, the transpose of design matrix and multiply by X. You remember the other time? Take a look at this. Give me 1 second. I'm going to clean this now. Now, let's see X. Do you see X, right? What would be the transpose? Converting row to column, right? Now, I want to explain how we get this in the first place. How do we get that guy in the first place? Getting this guy is the product of the transpose of X multiplied by X, which is going to be, take a look at this. You see the S transpose X. What is S? What is X? This is X. What is the transpose? This guy. If I do matrix multiplication, it's gonna be this guy. Okay. Now, if that is this guy, another thing is we've gotten this guy now, right? Then how do we get this guy? How do we get that guy? Summation y, summation xy. Okay, I'm going to show you now. It is S, it is the transpose of X times Y. What is the transpose of X? This one? What is Y? You know, I show you Y the other time, right? I show you Y. Let us do matrix multiplication. 1, 1, 1, 1, you know, 1 times this, 1, add all of them is going to be summation Y. And X1 times Y1, X2 times Y, and so on like that, add it together, that is summation. Who doesn't understand this? Now, the product of the transpose of X and Y give this. So if I now want to see the formula now based on this, it means this guy is S transpose X. This guy is S transpose Y. Because what we could have a situation where we're going to have, right now we're having 2 by 2 matrix, right? We're having 2 by 2 because we have 2 parameters. What of in a situation whereby the parameter is more than 2? It's not going to be 2 by 2 anymore. And that's why we need to know the general formula. So for this guy now, it is transpose of X times X. For this guy, the transpose of X times Y. Take a look at that. So, and that leads us to having this. Do you see that guy? That's a general formula now. If that's a general formula, we're looking for beta cap. That beta cap is going to be estimator, vector estimator. It will be beta naught cap, beta 1 cap. And somebody now say, okay, you know what? What am I going to do here is I'm going to come here. I'm going to pre-multiply this by this transpose X. Okay, inverse. The inverse of that. Okay, then this guy also gonna be here. When I say pre-multiply, not post, pre means that you are using this to multiply that. Does that make sense? And at the end of the day, take it, this guy is going to give you identity. Inverse of a matrix times itself is going to be identity. Identity times a matrix is still going to be that matrix. And at the end of the day, we got this guy. This is a general formula, which means in a matrix form, if I want to get the beta cap. That beta cap that you're seeing is a vector. It's going to give you beta naught cap and beta 1 cap. Now, the only challenge here is how do you get your inverse? Okay, the way we get inverse for 2 by 2 is different from the way we got inverse for 3 by 3. Now, take a look at this guy now. If I have this guy now, and I want to find the inverse, okay? Now, what I'm going to do is I'm going to interchange this. I'm going to exchange the element in the right diagonal. N is going to come here, summation S squared is going to come here, okay? And this guy is going to multiply by -1. They're not going to change. Divided by the determinant. Do you know how to find the determinant of 2 by 2? The determinant of 2 by 2 is distance this minus distance this. So the inverse is just going to be, okay, there's something that we call transpose of cofactor divided by the determinant, which is going to be this guy. Finally, it's going to be this guy. Now, in order to write it in a short form, this guy, we can call it COO, this guy CO1, this guy C10, and this guy C11. Please take notes. Okay, and of course, the covariance. So I need you to see something here. Okay, the variance of beta naught. You remember the other time we derived the variance of beta naught, the variance of beta 1, and the covariance of beta. So the variance of beta naught cap is going to be COO sigma squared. What is COO? This expression is COO. The variance of beta 1 cap is this guy and sigma squared. Okay, and this one is this. Now, if you understand that now, what we want to do, okay, we're going to apply. Okay, now, how do we write? Go ahead. For COO, you said is that sigma S. Let me see. COO is summation S squared divided by NXX. You welcome. That is COO. And of course, this guy is this guy, this guy is this guy, and this guy is that guy. Okay, please take note of the formula. Now, the next thing now is how in a matrix form, how do we write sum of square error? You know, in a scalar form, the sum of square error is this, right? Then in a matrix form, it's going to be this. This is y. Another way to write transpose is to just, this is a transpose now. Y transpose y. Of course, you know the vector y. The transpose of that is, so when you multiply, it's going to be y transpose y. Then you already know S transpose, X transpose y. Let me show you S transpose y. You see, S transpose y is summation y, summation x, y for simple linear regression. Okay, I think you can see that. Then your, look at this, beta cap transpose. Your beta cap is beta naught cap and beta 1 cap. When you find the transpose, you're just going to convert row to column. Okay, please take note of that. Now, you know what I want us to do now? If I have, why do we really need matrix? You know the other time, even without matrix, we're able to get the beta naught cap and the beta 1 cap for simple linear regression. But it will be complicated when we talk about multiple linear regression, situation where you have more than one explanatory variables. Take a look at this now. You know, take a look at this. That's a multiple linear regression where you have more than one independent variable. I remember when I was working on my capstone project in 2005, 6, yeah, where I work on the effect of exchange rate, consumer price index, and inflation rate on the GDP of Nigeria. So which means my independent variable is more than one. That's a multiple linear regression. Now, if I want to go by scalar, what we did the other time, this is going to be the sum of square error, right? And when you see this sum of square error, if you want to, in this sum of square error now, you want to find beta naught, beta one, beta two, up to, let's say for instance, you have like 10 independent variables. Okay, 10, you're actually going to have 11 numbers of parameters, which means I'm going to differentiate that with the respect to beta naught, with the respect to beta one, is going to take forever. Okay, so take a look at that. That's what we're going to do until you get to the last parameter. This is how the least square equation is going to be generated. Okay, now, okay, but do you know that if you can write it in matrix form, things will be easy? And you're going to see y still remain y, but x, what has happened here? You know, I need you to take note of this. If I'm dealing with simple linear, it's going to be 1, 1, 1, and just this rule. But now it's extended. This is like trying to say I have p numbers of independent variables. Does that make sense now? And take a look at my beta, my parameter. What has happened? I have from beta naught to beta p. How many parameters do I have? P plus 1 number of parameter, because it's always going to be beta naught. Error still remain the same. Now, what is the specification of multiple linear regression in matrix form? It is this. This specification, where y is this guy, x is this guy. The dimension of x is n by p plus 1. Okay, beta, this guy is all of this, and error is this. Is there anyone? Now, this is specification of multiple linear regression in matrix form. Any question? This is in matrix form. Okay, now, don't forget, this is the formula we're going to use. Now, you know what is going to happen? If I want to find it, if I use this, it's going to give me all the parameters at the same time, right? But I need to know x prime x. But the moment I know x, this is x, then I'm going to find the transpose of this guy. The transpose of this guy multiplied by this guy will give me s transpose x. Now, I'm going to have a matrix. I want to find the inverse. You can use your calculator to find the inverse of whatever dimension. But let me tell you this. This have to be a square matrix. Does that make sense? Okay, if I'm working with 2 parameters, it's going to be 2 by 2. 3 parameter, 3 by 3. 4 parameter, 4 by, and so on like that. Okay, so please take notes. Now, I want to walk you through an example now. You know, the other time in the last, we solve a simple linear regression using the formula for beta 1 cap and the beta naught cap. But right now, we want to use the matrix. Now, using the matrix, this is your y. This is what they give you, observations. X, we only have one x, right? One independent variable, which is -2 to 2. But you know why we have 1, 1, 1, 1, 1. That is for the constants. Any question about these two? Now, I need S transpose X. You know what I need to do? S transpose S for 2 by 2. Come back here. S transpose X for 2 by 2. I'm going to show you now. Do you see this guy? Please take note. And number summation X, summation X, summation S squared. All that you're going to get out from your data. Okay? So, and I'm also going to be needing S transpose Y, which is summation Y, summation XY. Now, let's go there now. Now, what is my 5 means 5 observations. Okay? Is 0 means summation X. Right? Add this together. What does that give you? 0, summation S. And whatever you have here is what you're going to have here. And this guy is summation S squared. When you square each of these, 2 squared plus 1 squared, -2 squared plus -1 squared plus 0 squared, all of that square, add it up, that will be 10. Any question? You get this guy now. What about S transpose Y? The first one is going to be N. The second one, summation XY. Do you see what you get? 5 and 7. Now, I need the inverse of this, which is this guy. You can use a calculator. Now, I'm going to use this guy to multiply this guy. Automatically, what do you see? 1 and 0.7. You remember that time? We got 1 and 0.7. Any question? Now, my beta naught cap is 1. My beta 1 cap is 0.7. Then plugging that into the model, I got that. This is solving simple linear regression model in matrix form. Any question? Using matrix approach. Any question? Now, I want to go into, take a look at this. This is a quadratic regression. Why? In addition to having beta naught plus beta 1x, I also have beta 2 plus s, beta 2s squared. That's quadratic in nature, right? That's a quadratic. At times, okay, relationship may not be a straight line, maybe a curve. Now, if I give you this, how do we represent this in a matrix form? Okay, this is my y. Maybe they give you they give you y to be this. They're going to give you just y and x. But you'll be the one that will produce this. 111 x, then s squared. That's super easy, right? Even if this guy go to cube, it's just going to be extending, right? Any question? Super easy, right? Now, the moment you get, your vector y and your vector x, every other thing is going to be easy. Now, I can now get my s transpose x. Transposing this, multiply it by this. Okay, look at that. Transposing this is this. And multiply by this. It's going to give us this. Okay. Now, after getting that, then we need to get S transpose y. You see that? That will going to give me this. What am I going to do with my calculator? I need the inverse of this guy, 3 by 3 matrix. Okay, the inverse of that is this. Calculator is going to do that. Then what is going to be my beta? The inverse multiplied by S transpose Y. So this is the inverse, S transpose Y. You're going to get 3 results. The first one will be beta naught cap. The second one is beta 1 cap. Third one is beta 2 cap. Then this is the model. Any question on that? That is the model. Any question? Now, there's something I needed to take notes. If you take a look at this guy, okay, the first number here is n. It's still n, 5, right? 1, 2, 3, 4, 5. You see that, right? This is the second one is summation x, summation s squared. Summation s squared. You see that? Go this way, go that way, the same. Look at that. You see that, right? Summation x is 0. Look at that. When you add this guy up, sum of s squared is 10. You see that? Okay. Now, if you get this guy, what about this guy? Okay. That is still that guy. Okay. So, but you don't have any issue. The major thing here is the moment you can perform this matrix. That is why they taught you how to do matrix multiplication. It's just going to be easy. Of course, if I'm going to give you this, of course, I'm going to allow you to use your calculator. Now, is there any question about this? Now, in this module now, I think before I go, I'm quickly going to interpret. For here now, we have linear effect and the quadratic effect. Okay, you see the one that measure linear effect, you see the one that measure quadratic effect. Okay, now if you go back to here, how do we interpret regression constant? That one, the regression constant, is just trying to tell you what is the expected value of the dependent variable when s equal to 0. And how do we interpret 0.7 here? Okay, for every unit increase in x, it is expected that the values of y will go up by 0.7. Why do I say up? Because there's a plus. If it is negative, is expected to decrease. But you have to say for a unit increase. Does that make sense now? Any question about what we've done today? Any question? Okay, there's not going to be lecture on Wednesday because of my talk, and I'm going to share you the link. I think I just shared some, and I'm still going to put the link out today. But I'm going to say we're going to have lecture on Friday. We're going to return to in-person. But by next week is going to be a revision where I'm going to show you what is going to come in the final. Go ahead. Which module on camp? Which one? What you didn't find what? Oh, you made a slide? I think I put it on. Give me 1 second. I It's on Canva. In fact, I put it on Canvas I put the PDF version uh sometime, and I put the let me check. Give me 1 second. Is there any other person that is not also seeing that on Canvas?
I couldn't find it on
Is there
Canva.
anyone? I'm opening the Canvas now. Module.
I couldn't find
Okay.
it.
I'm gonna see. Oh, it's right here. Do you see December 4? Oh, I can see what happened. My bad. Not publish. I can see. Sorry about that. Yeah, I'm gonna publish that now. Yeah, it's published now. Yeah, sorry about that. Okay. This way I'm gonna stop. Make sure you all stay safe and have a lovely day. Bye for now, everyone.